for Calc 1 for the next hour. If you guys have any, I have a few problems here. If you guys have any questions, let me know. I'd like for you guys to try some of these on your own as well. So I guess let's start from the beginning. Okay, so back, yes, sir.
Mr. Sotero asked if you take attendance because he's giving us a credit for this.
Okay, sure thing. See, I think we're supposed to get a sign-in sheet.
Yeah, we asked him that, and he said just have him take attendance.
Okay,
We're asking him to take attendance.
fair enough. So here's what I'll do then. See how I find out to take, huh?
Maybe he will do it and 10 extra credit.
Let's try now. All right, so I'm going to pass a blank sheet right now, and you guys can sign in, all right?
Thank you.
Ron, thank you for bringing it out. Anyway, so back in Chapter 2, we studied this notion of limits, right? Now, as you may remember, the idea is to look what happens to certain quantities as we approach certain quantities, right? So for example, here I have this function, this limit. We have the limit as x goes to 6 or the square root of 10. Now this is just a constant term, so what would the limit be?
As x goes to 6.
Yeah.
We need an x.
Well, it's just a constant term, right? So if you think of it in terms of the graph, here's the square root of 10. What happens as you approach 6 from both ends? What is the limit?
Square root of 10.
It is going to be square root of 10, right? It doesn't change. Again, that's because it is a constant term. Okay. Now, compare it to something like this. Here you have this limit as x goes to negative infinity of 10 times x squared minus 7x minus 6. In this case, what's going to happen?
It's going to infinity.
It's going to go up to infinity. Why?
The negative cancels out when it's squared, and that's going to be the largest number.
That's one way to think about it, certainly. I like to visualize it instead. I think this gives you a better understanding of what's really going on. So this is a parabola, right? No matter what parabola looks like, or what a parabola looks like exactly on the xy plane, what's going to happen as x goes to infinity? Well, as x goes to infinity, the outputs keep growing, right? So as the outputs grow, without bounds, this is going to explode, essentially. Right? And so that's why we have this limit at infinity. It's infinity. Now don't forget that this doesn't mean the limit exists. It doesn't exist. Okay? It's just to note the fact that as x grows without bounds in either direction, the y values or the output values will do the same. Any questions? Okay, so remember, one of the topics covered in the chapter was dealing with these limits at infinity and infinite limits. Okay, this problem combines both ideas. All right, so here's another example. And we're finding limits here, so in this case, you compute the limit as x goes to 2 of x squared minus 4 over x cubed minus 8. Now, how about this one? What are your thoughts on it?
You can't plug in the 2 because
You
you know equals 0.
Okay, well, the first thing you'd always do is you plug in the value, right?
Yeah.
And see what happens. Well, at first glance, if you plug in the 2, you get a 0 at the bottom. 8 minus 8. So that's not good. However, we also get a 0 on the top. So there's two ways to go about this. Okay? One way will be to think of this as an indeterminate form. Right? This is a 0 over 0 form. Okay, so we have this indeterminate form 0 over 0, which means that we might be able to use L'Hopital's rule. Now, according to L'Hopital's rule, we do what?
Is it derivative?
Derivative of what?
Oh.
The top and the bottom individually, right? You take the derivative of the denominator and the derivative of the numerator individually, right? So according to L'Hopital's rule, you're looking at the limit as x goes to 2 of the derivative at the top divided by the derivative of the bottom. Okay? And if you do it this way, then you're looking at the limit as x goes to 2 of 2x over 3x squared. Okay, questions? No? So at this point, what can we do?
Plug in the 2.
Plug in the 2. Now, what will happen if you get another indeterminate form? You can reapply L'Hopital's rule. Now, remember, that's not your only option. You might be able to simplify things around a little bit before you do. But yeah, essentially, you get an indeterminate form, there's a chance you may have to use L'Hopital's rule again. Anyway, in this case, we can just plug in the 2. We have a 2 times 2 over 3 times 2 squared. What is this limit equal to? 4 over 12, which simplifies to 1/3. Excellent. Questions? No? Okay. Was this our only option in this problem? Actually, no, it wasn't. If you remember in chapter 2, one of the things we learned was that in cases like this, when you're getting 0 at the bottom, you can do a few things. You could factor out if possible, see if things reduce that way. You can also multiply the numerator and denominator by conjugates. In this case, there's no need to do that, but it's one of the possibilities. Okay? In this case, this actually was reducible. You can factor out this difference of squares, and you can factor out this difference of cubes. Okay? So don't forget that because we have an indeterminate form, excuse me, don't forget that because we have an indeterminate form that we're stuck using L'Hopital's rule. It's not the only method out there. In fact, I believe the book says this. The book says that L'Hopital's rule should really be your last option. Okay? So don't go automatically to L'Hopital's rule every time. Any questions? No? Okay. So remember, sure comes in handy, but it's just one more tool in a tool set that we've been developing the whole semester. Here's another limit. So okay, so if we raise this half, guys? Yeah? Okay, so in this case, you're looking at the limit as v goes to 4 from the right of 4 minus v over the absolute value of 4 minus v. Now this one's a little bit trickier. Any idea why? Any suggestions? Because of the absolute value, you have to be a little careful here, okay? At first glance, if you plug in the 4, you get 0 over 0 in determinate form. But of course, I think this will just make the problem a lot harder than it needs to be. Okay? Instead, think about what the absolute value is doing. What is the absolute value doing here? Or what does it do in general? Sorry?
Making it positive?
It makes the number positive, right? So, in particular, let me ask you guys the following question. We are approaching 4 from the right, correct? That means that every value of v that we can think of needs to be bigger than 4. Because remember, we're approaching from the right. So, here's 4. We're approaching it from this direction. Okay? In other words, every number is bigger than 4. What does that tell you about 4 minus v? Specifically, sorry?
Should be negative?
Careful. If 4 minus v is, if v is bigger than 4, then what was that again?
It should be negative.
It should be negative, exactly, right? So you can see this by looking at this inequality. If v is bigger than 4, then 4 minus v will be less than 0. Right? In other words, as you're computing this limit, the expression 4 minus v is going to be negative. So how can we change this expression so we can get rid of the absolute value signs? Remember, the absolute value is just making it positive. So what's another way of making a negative number positive? Multiply by negative 1, right? So that's exactly what we wanted in this case. So, in other words, the limit as v goes to 4 from the right of 4 minus v over the absolute value of 4 minus v is equal to the limit as v goes to 4 from the right of 4 minus v over negative 4 minus v. Is that reducible? Can we reduce that expression? Yeah, it reduces down to negative 1. So this is equal to the limit as v goes to 4 from the right of 1 over negative 1, or simply negative 1. Any questions? No? Okay. Let me see here. That's right. Let's try a few more. So here's another limit, another kind of limit you see. In this case, looking at the limit as x goes to infinity of the square root of x squared plus 4x plus 1 minus x. Any suggestions here? Yeah, multiply the top and the bottom by the conjugate. In this case, of course, the denominator being 1. Okay? So let's give it a try. We're going to multiply the top and the bottom by the square root of x squared plus 4x plus 1 minus x over the square root of x squared plus 4x plus 1 minus x. Oh, sorry, plus x. And let's see what happens. So in this case, we have this limit as x goes to infinity of the top reduces down to x squared plus 4x plus 1 minus x squared. And the bottom is now the square root of x squared plus 4x plus 1 plus an x. Okay, and what we have here now is just this limit as x goes to infinity of 4x plus 1 in the numerator. Notice that the x squareds add up to 0. And at the bottom, we're left with the square root of x squared plus 4x plus 1 plus an x. Okay, guys. Now, how about at this point? Any suggestions here? Here we're looking at a limit at infinity, specifically as x goes to infinity. So you guys remember how to tackle those? Oh, remember that one of the techniques used, aside, of course, from L'Hopital's rule, is you look at the powers. Right, here we go into a response set of infinity, so we could divide every expression by x. Inside the square root, we should be dividing, of course, by x squared. So now you're looking at the limit as x goes to infinity of 4x over x plus 1 over x divided by the square root of x squared over x squared plus 4x over x squared plus 1 over x squared plus x over x. Now remember, the difference here between using an x and using an x squared is that the extra is being used inside the square root, right? And what is the square root of x squared for positive values of x? The square root of x squared. X, right? Okay. Good. So doing it this way and simplifying a little gives us the limit as x goes to infinity of 4 plus 1 over x divided by the square root of 1 plus 4 over x plus 1 over x squared plus 1. And so let's try to take the limit. What's going to happen to some of these terms? Say, for example, the 1 over x. That's right. This is going to go to 0. And this is going to go to 0. This is also going to go to 0. What are you left with? You're left with a 4 on the top. What about the bottom? Yep, square root of 1 plus 1, which is 2. Excellent. Any questions? No? Okay. Now, one of the things we learned in chapter 2 was something called the IVT. You guys remember what the IVT stands for? Intermediate value theorem. That's right. Now, you guys remember what the intermediate value theorem stated? What does it say? Well, intermediate values theorem said that if you have some function f, and that function f is continuous in some interval, okay, that you are bound to hit every value in between, that your outputs, are bound to hit every value within that interval. Okay? The easiest way, I think, to explain it would be to visualize it. So, now let me see, I want to try to erase the whole thing in case some people start writing. You think of some graph f of x. Okay, and this here is A, this here is B. So this is f of A, f of B. Then all the intermediate values theorem says is that since f is continuous, you'll have one curve between A and B that hits every single real value in between f of A and f of B. Okay, as an output. Okay, and often this term was used to solve problems like the following. Using intermediate value theorem to show that there's a root of the equation in the given interval. So you will be giving an equation say something like give me just a second, in the given interval. Something like the cosine of the square root of x is equal to e to the x minus 2, and you had to prove that, that there is a root in the interval from 0 to 1, for example. Okay, well, proving that there is a solution to this equation will be equivalent to showing that there's a root for the function f of x is equal to cosine of the square root of x minus e to the x plus 2. Of course, we're keeping the interval the same. Now think about these functions. Cosine of the square root of x, e to the x. Are these functions continuous from 0 to 1? They are, right? I mean, the only thing that could cause any sort of trouble will be the square root, but that trouble only comes when you deal with negative numbers. In this case, there's no negative numbers to deal with, so we're good. So it's easy to see that it's continuous from 0 to 1. Any questions though, or any trouble visualizing that? No? Okay, so we know that f of x is continuous from 0 to 1. Okay? In fact, I think here actually we have brackets in a closed interval from 0 to 1. Now the idea with the IVT is to show, in particular using the 0 and the 1, that if you get a positive and a negative number, then for outputs, then you're bound to hit 0 at some point in the middle, right? It's bound to happen. You don't know when or where, but it's bound to happen. And that's all we're showing here. So in this case, we know a few more things. F of 0, for example, will be equal to the cosine of 0 minus e to the 0 plus 2. And what is that equal to? Well, this is 1, 1, 2, exactly. So this is 2. Now, what about f of 1? Well, f of 1 will be cosine of 1 minus e plus 2. Is this positive or negative? Or actually, what is this equal to? For this one, you will have to use a calculator. Make sure it's in radians. Okay, so you get negative 0.18. So in this case, you get approximately equal to negative 0.18. Okay, which is good. Note that at this point, what's not so important is the actual number, the magnitude of the number. What's important here is that we got a positive and a negative. Okay, and that is crucial to be able to finish this problem. Okay. Okay, so in this case, since f is continuous, the immediate value theorem states that there is some c in the interval from 0 to 1, open interval from 0 to 1, okay? So that f of c is in between 2 and negative 0.18. So actually, let me go ahead and make myself some more space here. Now, in particular, here what we're interested in is a 0, right? Now, here we have a negative number and a positive number. So what this is actually saying is that we have some value of c in between 0 to 1, so that f of c being 0, the root, is in between those two values. Okay? Remember that in this case, we're choosing c so that f of c is 0. Okay, any questions? So it is good to go back and review some of these theorems. I mean, you guys are now at the point where you're going to see some really powerful theorems out there in calculus. And it would be good to remember some of these every once in a while. Okay? Okay, any questions with the intermediate value theorem? No? Okay, one of the other things that is worth remembering is the definition of a derivative. So let me ask you guys, what is the definition of a derivative? Well, it's a limit, right? Now, a derivative is defined remember, the derivative is defined to be the limit as h goes to 0 of f of x plus h minus f of x all over h, provided that the limit exists. Okay? So what I want you guys to do now, actually, is use the definition of the derivative to find f prime of 2, given the following. Yes, I want you guys to find f prime of 2, and I don't want shortcuts here. I want the actual definition of the limit of the derivative, right? The limit definition. Okay, so let's go ahead and set it up. Well, this means that f prime of 2 needs to be equal to this limit as h goes to 0 of f of 2 plus h minus f of 2 all over h. Okay, so what do we do next? Just plug it in, right? So you're looking at the limit as h goes to 0 of x plus h quantity cubed minus 2 times x plus h minus f of 2. F of 2 being, of course, 2 cubed minus 2 times 2 all over h. Any questions? Yep. Okay, so we can simplify this a little bit. We're going to have x plus h quantity cubed minus 2 times x plus h minus, this is going to be 8 minus 4, giving you 4 over h. There's more stuff we could do. For example, we can expand x plus h. Okay, and if my memory serves me right, that expands out to x cubed plus 3x squared h plus 3h squared x plus h cubed Okay, minus 2x, minus 2h, minus 4. So I'm kind of running out of space here. Let me go ahead and erase this half so I could write it out. So this is what we have. We have this limit as h goes to 0 of x cubed plus 3x squared h plus 3h squared x plus x h cubed minus 2x minus 2h minus 4 all over h. All right, any questions?
How do we get rid of the h over here?
No, I didn't. I just didn't have enough space to write it all out. So I moved over here. So let me go ahead and erase this. Okay, so that's what we have, and I just moved it over. Okay, so at this point, now I didn't do it over here, but at this point you could replace the x's with 2's, right? And simplify this problem quite a bit. So now you're looking at the limit as h goes to 0 of 2 cubed, which is 8, plus 2 squared, which is 4 times 3, which is 12, so 12h, plus 3 times 2, which is 6, h squared, plus h cubed, minus 2x, sorry, 2 times 2, which is 4. Minus 2h minus 4. Okay? And you see that a lot of things should start to vanish. For example, the 8 and the 4's add up to 0, right? What else? Sorry? So here you have 12h, here you have minus 2h, right? So it's going to reduce down to 10h. You have 10h plus 6h squared plus h cubed over h. And this whole thing reduces down to the limit as h goes to 0 of 10 plus 6h plus h squared. So what's the limit? 10. Okay, good. Okay, so any questions?
So when you put in the 2 in the right equation, like 2 to the third minus 2 times 2,
Yeah.
could you technically leave it as x?
Well, you could leave it as x and plug in the 2 later, or you can plug in the 2 from here and go on. It won't affect the answer.
Okay.
Yeah. Any other questions? No? Okay. Let's see. Now, of course, we all know that using the definition of the derivative may take a while, right? Makes some of the problems quite a bit longer than they need to be. So now, let's go ahead and use our shortcuts to compute a few derivatives. All right, so compute the derivative of the following. Let's see. Let's start with something simple. How about something like this? There's a few rules involved here, right? Can you guys name a few? Sorry?
Chain rule.
Chain rule, okay. What's another one? Product rule. Yeah, so there's a combination of the product rule and the chain rule. All right, so let's give it a go. y prime is going to be equal to what? Okay, I heard 2x, so 2x sine of pi x. What else? Plus. And
The chain rule for the x.
well, we took the derivative of this portion, right? So we leave the sign as it is. The next part, we leave the x squared as it is, and we differentiate the sign. And that's where the chain rule comes into play. So we're going to have x squared times the cosine of pi x times pi. Good. So here's what you're looking at. Questions? No? Okay, so let me see here. How about this one? So what kind of rule should we use here? The quotient rule, that's right. So according to the quotient rule, what's my denominator like? It's going to be the denominator squared, right? t to the 4 plus 1 quantity squared. Excellent. Now what about the numerator? So I heard the 4t cubed, so you have to speak a little louder. Exactly. So this is the derivative of the numerator. I'm going to multiply it now by the denominator. All right. What next? Times what? Yep. The numerator, right? Good. All right. Any questions? No? All right. So let's try to simplify it a little bit. Make it look a little prettier. 4t to the 7th plus 4t cubed minus 4t to the 7th plus 4t cubed. Of course, some of these will add up to 0, but you're left with y prime is equal to 8 t cubed over t to the 4th plus 1 quantity squared. Good. Any questions about the problem or the chain rule? Okay, so remember, there's quite a bit of rules we talked about, right, throughout the semester. We talked about the product rule, chain rule, quotient rule. What other rules are out there? What other rule did we use, say, for example, right here?
Power rule?
The power rule, that's right. We used the power rule. And there's many other rules out there. Now, in particular, there's one rule I'm thinking about that can be particularly useful if you know how and when to use it. So here's another kind of problem to get us started on that. Y equals to 3 to the power of x natural log of x. Now, one of the possibilities to do here is a combination of the chain rule and the derivatives for logarithms. Okay? I don't want to go down that path. Instead, I want to use this example to remind you guys of implicit differentiation. Okay, for example, in this case, you could very well take the natural log of both sides. Why? Well, you take the natural log of both sides. What's going to happen to this exponent? That's right, we're going to be able to bring it down to the front. And so now you're looking at the natural log of y is equal to the natural log of 3 times x natural log of x. Now, technically it's a multiplication, and since multiplication is associative, I can write it down in any order I want. Sorry, commutative. Anyway, the natural log of 3 is a constant, right? So we don't need to worry about that part now. Of course, we have the natural log of y here, so we're going to have to differentiate implicitly. So let's try it. So according to implicit differentiation, if I take the derivative of both sides with respect to x, what am I going to have on this side? Sorry? Yep. 1 over y times y prime. Excellent. All right. And now we just need to worry about this side. And we could use, for example, the product rule, right? So for example, we could group these two together and then just deal with the natural log of x separately. So what is the derivative of the natural log of 3 times x?
1 over x.
Careful, the x is outside the natural log. And the natural log of 3 is just a constant. It's going to be the natural log of 3, right? Because remember, this is just a number. So the derivative of this is going to be natural log of 3. Times the natural log of x plus this is the derivative of the natural log of x, which is what? One over x. Good. Okay, so I'm going to multiply both sides by y, and you get the y prime is equal to y times natural log of 3 times the natural log of x plus the natural log of 3. Not to mention that we know what y is equal to. What's y equal to? 3 to the power of x ln of x. Okay? So in this case, your derivative is 3 to the power of x natural log of x times the natural log of 3 natural log of x plus the natural log of 3. Now, any questions on this one? No? Okay, so let's see. Remember, one of the things that made the derivative so useful is that we could now talk about rates in terms of other rates. Okay, so for example, we could have a related rates problem. And let me see. In this case, for example, you could look at the volume of a cube. The volume of a cube is increasing at a rate of 10 centimeters cubed per minute, for example. how fast is the surface area increasing? When the length of the edge is 30 centimeters. Now, one of the difficulties in these sort of problems is that you have to remember a few formulas from geometry. For example, in dealing with a cube, the volume of a cube will be x cubed, right? X being this length of an edge. The surface area will be something like 6x squared because there's 6 sides to a cube. And each side has an area of x squared. X, again, of course, being the length of an edge. But of course, we're limited to those formulas. You guys may have seen problems that deal with cones, right? So those are other formulas worth remembering. If I remember correctly, the volume of a cone is what, 1/3 pi r squared h. Okay. Volumes of a cylinder. How to find the surface area of a cylinder. Those are all particularly useful formulas when dealing with related rates. And actually optimization problems as well. In this case, we're dealing with a cube. And as I mentioned, the volume of a cube is simply x cubed, where x is the length of an edge. Okay, the surface area is given as 6 times x squared. The easiest way I find to think about this is to remember that because we're dealing with a cube, there's going to be 6 sides, and each side is a perfect square, right? It's a nice little square, and every square is going to have an area of x squared, right? There's 6 of them, so you add them all up, you get 6x squared. Okay, so using these now, we can answer this problem. How fast is the surface area increasing when the length of the edge of an edge is 30 centimeters? So how do we do these problems, guys? What do you recall? You have to compute a derivative. A derivative with respect to what variable? Not x, actually. Well, remember that with related rates, you're always taking the derivative with respect to a third variable, right? Typically, time. So that means that whenever you compute a derivative, say for example the derivative of the surface area, you're going to end up with using implicit differentiation. So say for example we take the derivative of this with respect to time. We're going to have ds dt is equal to the derivative of this, which is going to be 12x times the derivative of x with respect to time. Okay? Now, let me move over here. What else do we know? We know that the volume is equal to 10 centimeters, or sorry, the volume is increasing, so dV dt must be 10 centimeters cubed per minute. Okay? So that means we also need to look at the derivative of the volume and how is the volume changing over time. In this case, since v is equal to x cubed, then that means that dv dt must be equal to 3x squared dx dt. So notice, the problem is asking for the rate at which the surface area is changing, right? It's asking for this quantity. Now the problem here is that to be able to find this quantity, we need this quantity, right, the x dt. Here's how we're going to get it. We're going to get it by looking at how fast the volume is changing. Now the volume is changing at a rate of 10 centimeters cubed per minute. So we're going to take this, plug it in there, and since we know what the length of the edge is at that precise time, we're going to plug in 30 centimeters in there. Okay? So let's do this. We're going to have 10 is equal to 3 times 30 squared times the x dt. All right, now I don't have a calculator with me, so what I'm going to do here is I'm going to solve for the x dt as it is. I'm going to have 10 over 3 times 30 squared. Now 30 squared is 900, right? So this whole thing is going to reduce down to 10 over 3 times 900. Okay, now thankfully I know how to reduce that. There's the 0 goes away there, and you have 1 over 3 times 90. 3 times 90 being 270. So this is 1 over 270 centimeters per minute. Okay, now that we have the x dt, we can actually plug it in. Remember that this is how fast the edge is changing. So we gotta just plug it in here. We can find the rate at which the surface area is changing. Okay, so here we go. We're gonna have 12 times 30 times 1 over 270. Okay, now these have a common factor of 30. Okay, so this reduces to 1/9. I'm going to have 12 times 1/9 here. Of course, those have a common factor of 3. So this actually reduces down to 4/3. Questions? Now, okay, what are my units, by the way? This being surface area. Centimeters squared per minute, right? It's a rate. Now, any questions? Nope. Okay. Let's see here. I don't think I dispose with very much more time. So let me go ahead and jump a couple of sections. And, you know, actually, before I do, there's a few things that are always worth remembering in calculus in terms of limits. And so let me write this down. Remember that in general, as x goes to either plus or minus infinity, 1 over x to the n, that's always 0. Another limit always worth remembering is the limit as x goes to 0 of sine of x over x is equal to 1. And another one that is worth remembering is that the limit as x goes to 0 of 1 minus cosine of x over x is equal to 0. Okay. These three limits are some of the ones that are worth remembering. So keep in mind those, especially this one. Okay. Especially the sine of x over x. That one can be Very useful. Okay, so let me make a quick jump over to chapter 5, seeing how that's the newest stuff we've covered. And let me ask you guys the following question. How can I rewrite this as a definite integral? On the interval from 0 to pi. Again, the idea is how can I rewrite this as a definite integral? Okay, the integral sign, all right, fair enough.
And for the upper bound, you put pi. For the lower bound, you put 0.
All right.
Then you put
Sine of x. Well, remember the xi changes with an x. And instead of delta x, we're going to have a dx. Excellent. Good. All right. Go ahead and find it, please. $130? Okay. Sorry? Okay. Okay, what is the integral of sine of x, or the antiderivative of sine of x? Negative cosine of x. So here you're looking at negative cosine of x evaluated from 0 to pi. Okay, so you're looking at the following. You're looking at negative cosine of pi plus cosine of 0. And what is that equal to? What was cosine of pi? Negative 1. Negative cosine is positive 1. So here you have 1 plus 1. And so this is equal to 2. There you go. It's a fancy way of adding 1 plus 1, right? Okay. Any questions? Yeah? Okay, let's do a few more things with integration then. How about this one? Find the derivative. But I'm going to give you guys a function capital F of x as being the integral from 0 to x to the 4th of the cosine of t squared dt. And again, you have to find f prime. Basically, this problem requires you guys to remember the fundamental theorem of calculus.
You said something equal to you.
Hmm? Sorry?
Or you said something equal to you.
No, not quite. Now remember, as the name implies, the fundamental theorem of calculus is kind of a big deal, right? And so it goes without saying, it's probably one of those things, the top of your list of things to remember. Okay? In particular, the fundamental theorem states that integration and differentiation are inverse processes, right? In other words, the derivative in this case would just be the cosine of, instead of t squared, an x to the 4th quantity squared Okay, this has to do, remember, with the first part of the fundamental theorem. The cosine of x to the 4th quantity squared times the derivative of x to the 4th. After all, we do need to apply the chain rule here. So you're looking at the cosine of x to the 8th times 4x cubed. Any questions? Nope. Okay. Now, when it comes to integration and anti-differentiation, remember there's one thing you need to be careful with. So say, for example, I'm taking this integral, indefinite integral, say something like, I don't know, x squared plus 7x plus 6 dx. What is the integral of that? Careful, not quite. Sorry? X cubed over 3. 7x plus 6. That's right. That is what I wanted to remind you guys. Remember that when you're dealing with an indefinite integral, you always need to add a plus c at the end, right? Anti-differentiation or integration, indefinite integration, produces a family of integrals or a family of functions. Okay, not just a single one. So you always need to have that plus c there. Now, remember that the only way you can get rid of a c, or a term like this, will be whenever you have some sort of initial condition. Right? I don't know, in this case maybe that will be equal to 1 when x is 0, for all we know. And then you have to use that to solve for c. Now, any questions? No? Okay, so now let me give you an example from section 5.5. I think that's pretty much the newest stuff, right? So here's what we have. Let me see here. Let's do the integral of secant theta tangent theta over 1 plus secant theta d theta. Now, I don't know if you guys remember, but section 5.5 deals with what is called substitution, right? Sometimes we refer to it as U substitution, or U sub for short. And the idea is to replace one of the expressions in the integrand with a new variable and make the corresponding changes, right? And evaluate another integral and then go back to the original expressions. In this case, for example, it will be a good thing to substitute.
1 plus secant theta.
Yeah, 1 plus secant theta. In this case, for example, I'm going to let my u be 1 plus secant theta. And if I do that, what's the differential of u? What is du equal to in this case? Well, what's the rate of secant? Secant theta tangent theta, exactly. So du is equal to secant theta tangent theta d theta. Okay, there's a differential of u. So notice that we have, let's see, let me find another color. It's the black. We have this right here, and we have this right here. Okay, so this whole integral can actually be written in terms of u as the integral of 1 over u du. And what is the integral of 1 over u? Is the natural log of u, right? To be precise, guys, is the natural log of the absolute value of u. Okay, so this is simply ln of u, absolute value of u, plus a constant. Of course, we need to replace the u, right, with a substitution. In this case, that means that our answer is the natural log of the absolute value of 1 plus secant theta plus a constant. Questions?
Your conference is scheduled to end in 2 minutes.
Okay, so any questions on any of the stuff you guys seen today? Now, it was sort of a comprehensive review of a few things. Remember that we only had an hour, so there's only so much material we can cover, right? So other things you guys should probably pay attention to are things like optimization, right? It is also a pretty good skill to be able to graph functions based on information given by their derivatives, in particular the first and second derivatives, right? Things like the ID test, where is things increasing and decreasing, the concavity test, the first derivative test, the second derivative test. Okay, those things are also very useful. And I believe that's about the only things we didn't get to cover today. Oh, and the mean value theorem, of course. That's another one worth taking a look at. Okay? Again, any questions? Nope? Great. Well, you guys have a wonderful day. Good luck on your finals.